Hello all, can someone write me if you can hear me? Okay, I hope the sound is clear, so let me introduce myself. My name is Mantas, I am from company Energy Advice, I am projects manager working here for around 5 years, and basically today I am going to talk about the protection coordination in electrical networks with EA-PSM software. So last trainings was about the general functionality about the software. Now we will concentrate in this more concentrated topic about the protection coordination. Just to begin with, for those who haven't participated in the latest trainings, let me introduce the area where we are working. So as you can see, basically our company as a developers of the software, we have clients in various countries, United Kingdom, Spain, Italy. Those are the biggest countries in Lithuania. In the Europe, I mean. Also we have a branch office in Mumbai, India. You can contact people there for software license or demo license as well. For demo license, you can also visit our site to download and proceed working with the software. So as I have mentioned, the software has a lot of functionalities. Here we have only the main of the functionalities, but today we will talk about the protection functionalities, so protection and automation features. And in order to do protection coordination, you actually need almost all the calculations, so short circuit, load flows, arc flash calculations, also protection tracking, all these needed for protection coordination study. So Vikas is saying that there is an echo in the sound. Can someone else confirm? Should I try to change some settings? Or is good enough? Yeah, so you can write in the chat. So during these trainings, you can write questions in the chat, and my colleagues will help to answer the main questions regarding the software and technical questions. I will try to read and answer. So in the middle of the trainings, we will do a break for answering the questions. So you can maybe try to ask technical questions more in the middle of the seminar, so I will be capable to answer and read them. That's good enough, it says. So maybe it depends on internet speed. Also, you can change in YouTube video quality. So later on, you will be able to also relook all the seminar, because in YouTube the trainings will be for some time, so you can look also later on. So these are the second trainings regarding the protection coordination, and also there will be a third free webinar about the harmonics mitigation. This will be held in the 2nd of July. And during this third webinar, we will analyze power quality issues. So basically, for example, we will solve questions like what is the data needed for harmonic calculations, what are the harmonic mitigation techniques, how should report of harmonic mitigation and power quality should look like. So this is the short advertisement of the another free webinar, which will be next. So today we will talk about the protection coordination, and next time about the harmonic mitigation. Also, electrical network studies is not that easy, and electrical engineering covers a lot of topics. And in order to go in more details regarding the electrical engineering, so we invite into online EA-PSM Academy. These will be 16-hour trainings with EA-PSM electric software, and during these trainings we will solve practical cases. We will analyze theories regarding electrical engineering. Participants of the trainings will get EA-PSM electric for free for a 2-month period. So because of that, software is also actually, because of that, trainings are also have a price, so it's 290 euros if you will register till the 3rd of July. So you will get a discount in that case. Also, users of the software will get a 50% discount from the trainings, so you can just rent the software, and the trainings will be much cheaper for you. So for more details about the trainings, you can check our website, which is www.energyadvice.lt/en, so for English, and /training. Here you'll find all the free and also not free trainings which we are doing, and you can also contact us by the email info@energyadvice.lt or through the phone number. Okay, so here are the other contact details like Skype ID and our address. So this is the general information regarding the trainings, and now we can proceed further on to the technical trainings of the protection coordination. I can close the PowerPoint presentation. So to begin with, first of all, let's look at the electrical network. So short introduction about the network. Network starts from high voltage side, so it's 110 kilovolts network. Then we have a transformer, 25 megawatt amp transformer, which reduces voltage from 110 the medium voltage level 6.3 kilovolts. So in some factories this kind of voltage level is quite often used if they have powerful equipment, and connecting this kind of powerful equipment from low voltage network would be impossible due to high current levels. So 6.3 kilovolt voltage level is quite often. Then we have also grounding transformer. So basically, please notice that the main transformer has isolated neutral delta winding in 6.3 kilovolt voltage side. However, in order to provide grounding for the network, there is separate transformer used with 9 ohms resistance, and this resistance gives about 400 amps of one-phase short circuit current. Later on in the calculations we will see what is this resistance and how it affects the results. Then we have a breaker already with quite a few protection functionalities. Here are 2 stages of overcurrent protection devices, then under voltage, over voltage, and ground fault protection 2 stages as well. So here we have also a 6.3 kilovolt network consisting of 3 cables, 500, 300 and 200 meters in length. And we also have some equipment connected, like powerful over 500 kilowatts motor. Then there is a solar power plant, 1.5 megawatt, and one 2 megawatts transformer. So usually in this kind of big factories there are much more of these transformers, but for our example we will use only one of the transformers. And this transformer reduces voltage to 400 volts, so to a low voltage side, to low voltage network. And basically in our software, as you can see, it's possible to model several different voltage levels. So it can be high voltage, medium voltage, and low voltage, all together connected in one single line diagram. So you can do calculations of basically any network. So in low voltage network we have again cable lines with protections for low voltage protection for low voltage devices. And there are different kind of low voltage devices. So for example, here we have inverter. Basically it could be like variable frequency drive. Here we can see one more variable frequency drive, just a more advanced model where we have the variable frequency drive plus the motor connected. Then we have motor directly connected to the network, and finally we have capacitors connected through the tuned harmonic filters. So we will talk about the tuned harmonic filters also in our next trainings. So this is our network example, and today we will basically work on protection coordination in this electrical network. So let's start from the main principles of the protection coordination, and I would distinguish three main principles. One of them is protection devices sensitivity. Sensitivity means that if we have a short circuit, protection device should be capable to sense the short circuit current, and we have to select protection device so that its setting current should be low enough to be capable to distinguish the short circuit current. So for example, let's calculate a short circuit in our network. I will choose this bus 10. So we see that we have short circuit currents calculated in the minimum mode. So minimum short circuit current in three-phase short circuit level is 20. Here's the maximum. So minimum 21,700. Yeah, so this is the short circuit current. And here is our protection device, which nominal current is 600 amps. So now we can compare our protection device nominal current with the short circuit device with short circuit current, and we can clearly see that our nominal of the protection device is much less than our short circuit current. So which means that our protection device will be sensitive enough because its pickup current will be much smaller than short circuit current. However, if for example we will have very long cables and the short circuit current, for example, will be close to, let's say, our nominal level of the protection device, so then our protection device will not be sensitive enough. So sensitivity principle will not be maintained. And usually this happens when we have single line short circuits, so one phase short circuits, and because of for example a high impedance path from the short circuit location to the transformer, one phase short circuit current can be very small, and our protection device can be not sensitive enough to find this kind of short circuit. So the first principle is sensitivity. The next important principle is basically reliability of the protection devices, and what this requires from us, that protection devices should have backup protection. So we can see that, for example, this cable and this motor is protected by the circuit breaker here, again 600 amps. However, if this circuit breaker for any reason won't work, so maybe some failure of the breaker, maybe someone instead of the breaker put just the bar, metal bar, and connected the bus bars, so the breaker does not exist. So there should be another breaker which will trip in case of the short circuit. And in this kind of network, if we'll go further on, we can see that there is one more breaker, which is in the feeder, on the feeder of the section here. So this breaker is actually working as a backup protection for all the protections here. Yeah, so these fuses, breakers, overload protections, they are protecting the cables, and the backup protection is here. So basically, if there will be some problem with any of these protection devices, so we hope that this one will work. So this is the reliability of protection devices, which is again a very important principle. And lastly, but very important, last but very important also feature of protection devices is selectivity. So what does that mean, selectivity? Again, let's take the same line as an example. If I have short circuit in bus 10 or in my motor, so basically I want only this line to be disconnected. Also, because if protection devices won't work selectively, what will happen? For example, it might happen that incomer protection device, this breaker, will disconnect, and basically all the other motors, protection coordination, also reactive power compensation devices, inverters, all the loads will be disconnected from the network. And in the best case scenario, only this protection device should have been disconnected. So selectivity principle is to disconnect only those protection devices that are facing failure, that are facing short circuit or other problem, and we should not disconnect other protection devices that are working in normal mode. So in order to ensure that after the disconnection of the protection devices, all the good equipment will still be working. So this is the last principle of the protection coordination in electrical networks. So now, what are the calculations that we need for the short circuit, that we need for the protection coordination? So basically, I will quickly look through the list of those calculations. The first of all, it is power flows. Yeah. So when we calculate power flows, we get very important information for protection coordination, which is nominal current, or like a normal current in the electrical network during normal mode of operation. So for example, for this motor, normal current is 301 amp. So we must ensure that our protection device nominal will be bigger than this normal current, and that pickup current for this protection device will be also bigger. So basically, our protection device should not trip during this kind of normal mode. Next calculation that we need for protection coordination is different type of short circuits. So for example, if we do ground fault protection, so we need information about one phase short circuits, and because ground fault protection is measuring zero sequence currents, so we need information especially about the zero sequence currents in the electrical network in case of one phase short circuit. Then there are three-phase and two-phase short circuits that again needed for different cases. Two-phase short circuit is needed for setting protection devices, and like three-phase short circuit is needed for equipment selection, like busbar selection, also breaker capability selection, because we need to make sure that breaker will be capable to disconnect short circuit current even in maximum worst case scenario, so in maximum current. Then we also need motor starting, and motor starting is a tool that allows to estimate what are the currents flowing in the network during motors starting. And basically you remember maybe that in this line during normal operation current was about 300 amps, and during motor starting this current can reach up to 2.8 kiloamps, so 2800 amps. And this calculation that I have used here was simple motor starting. So this is a more conservative calculation that usually gives bigger motor starting current, and also it does not allow to estimate motor starting time. However, for more detailed analysis, we can also use motor dynamic functionality. So in our software, we have this feature which allows to calculate motor starting. Let's maybe try this functionality. I will set step time and calculation period time to estimate what will be the motor starting current and motor starting time. So as I have mentioned, while simple motor starting gives more conservative results, this motor starting gives more accurate and most cases less conservative results, but they are more accurate. So for example, here we can see that motor starting current is about 2000 amps. Here's the stator current, this blue one, yeah. And the motor starting time is around 10.5 seconds. So our protection devices should be capable to withstand this kind of current for at least 10 seconds, because otherwise if we will set our protection devices below motor starting curve, so during motor starting our protection devices might trip. Here is the slip, by the way, curve, this orange one, which is showing that at this point motor reached its nominal speed and actually slip is very low, so basically motor is started at here. So these calculations are very important for protection coordinations, and I would say that these are like classical calculations. However, in nowadays we can also use arc flash protection calculation. While we have softwares, so it is easy to calculate short circuits, also easy to estimate protection operation times. So in our software also automatically users can find what is the short circuit current, what is the operation time of the protection devices, and this allows us to calculate arc flash. And arc flash is related to human safety, basically by reducing disconnection times of the protection devices, we can increase human safety and reduce arc flash distance. So in order to avoid the injuries of the personnel who is working with the electrical networks. So all these calculations today during webinar we will use. So basically now this is just a quick review. So let's go then later on with the protection coordination itself. I think that I will start from the low voltage network protection coordination, and step by step we will move also to medium voltage as well. So as I have mentioned, for our protection coordination study we will need power flows, short circuits, result calculations, also motor startings. So I already calculated motor starting currents for this motor, so we will use them and I will not recalculate them. So let's start from the inverter protection coordination. So inverter as the device is very sensitive to imbalanced voltage and also to low voltage. So because it's so sensitive to these kind of conditions in the electrical network, so most of the inverters already have under voltage protection devices incorporated inside. So basically, because when we have low voltage conditions, currents inside the inverter and inside the thyristors of the inverter increase, and because of that inverter starts to overheat. So in order to avoid this kind of scenario, inverters already have under voltage protection devices incorporated. So usually we don't have to set any settings for the inverter protection, except maybe for solar inverters, where we can provide also disconnection times. But normal inverters like variable frequency drives, they already have under voltage protection devices, and if we have short circuit somewhere in the network, let's say, let's calculate short circuit in bus 10, so we will see that we will have lower voltage than normally. So normally in this kind of network our voltage should be around 230 volts, and now we can see that in case of three-phase short circuit in calculated area in here, so our voltage will be only 118, so much smaller than 230 30 volts. Then in two-phase we will have voltage which is equal to 111. In one phase voltage will be equal to 153, and here in two-phase with ground it will be around 117.5. So we can see that in all of these possible scenarios voltage will be much lower than nominal, and after some time inverter will automatically disconnect. What is more, we know that during short circuits voltage becomes unsymmetrical, so unsymmetrical conditions are also very bad for the inverter, and therefore inverter has protection from that already. So all we need for the inverter actually protection is to protect the cable which is connecting inverter with the main bus bar. Yeah. So if we will have short circuit in the end of the cable, we should have some protection device which will quickly disconnect that short circuit. So the most the less expensive device for protection coordination is fuse, and you can see that already I have fuse selected here. So its nominal current is 160 amps. So how I have selected the current for the fuse? So there are several possible ways. One of them is just to make sure to read the manufacturer datasheet and of the inverter. So in the inverter datasheet you most often can find what is the recommended fuse rating. Or another way to do that is using our software to calculate what is the normal current for the inverter. So we can see that normal current is 149 amps. So this means that we need to select fuse with a bigger nominal than normal current, so that our fuse will not disconnect during normal operation. So I will open the fuse one more time to show you that we have the library of the fuses as well. So we select from the list the possible protection fuse, and here we select fuse library, and here we have several manufacturers for the fuses. User can also add fuses, or best way to do that so is just to simply send us the fuse library, and we can incorporate that automatically using tools that we have. So let's say from the AT manufacturer library, let's select the general purpose fuses, and here we have several different nominal fuses. So the first one, which has bigger nominal than the calculated current, is 160 amps. So basically we can just simply select this fuse. This is done previously already. We can push apply, and already we have our protection device selected. However, when we select protection device, we also need to actually check how this protection device will protect our cable. So to do that, we can go one more tab back, and we'll go to chart tab. So in this chart tab we have several very important curves provided. So let's start by introducing those curves. So first of all, this red dashed line, what it shows normal current, which we have calculated. So the idea is this, that our protection device, any protection device, should have bigger current rating than our normal current. So we can see by the protection device current and time curve that our fuse definitely have a bigger current. So you can go down here. So on the lower axis we see that there is current axis. So our fuse current pickup is much bigger than our normal current, which is good. So basically our protection won't trip during normal operation. Here on the right side we have one more dashed line, which is in a gray color, and this dashed line shows a short circuit in the end of the cable. In this case not in the end, but in the beginning in the cable. So this current equals to 30,000 amps. I can see this by moving my mouse cursor, and it provides maximum possible short circuit current. and basically our protection device should be capable to protect equipment from this maximum short circuit current. How we can estimate if our protection devices are protecting the equipment? So on the line here we also have, on the picture here we also have a short circuit capability curve. And this short circuit capability curve, which is provided in purple color, is showing how much time it will take for cable. In this case it's cable, but in some other cases it can be transformer or other type of the equipment to overheat during the short circuit. So for example, if our short circuit current is 2000 amps, as we can see here in the lower axis, let's move up to the capability curve, and we see that our overheating time is around 20 seconds, a little bit more than 20, something from 20 to 30 seconds exactly. We can see basically on the bar here. Let's turn it on. It's around 25 seconds. Yeah. So our protection device, in this case fuse, should be capable to trip faster, and we can clearly see that in case of 2000 amps, our protection device fuse will trip something in around 180 milliseconds, which is good. It means that it trips faster and protects our cable. So this is the idea regarding the protection selectivity chart. First, we need to check whether our protection devices are capable to protect our equipment. So in case of the inverter, the only protection we need is actually the protection for the cable, which is connecting inverter with the network, and the cheapest way to do that is to use a simple fuse. Now let's go to other devices. So let's take motor. And motor basically has much more requirements regarding the protection coordination. First idea regarding the motor is that it is very sensitive to unsymmetrical operation of the network. So for example, if we have unsymmetrical voltage, let's say 5% unsymmetrical voltage, so this would cause motor overheating of about 40 to 50%. So only 5% of unsymmetrical operation of the motor will cause very huge overheating for the motor. So basically for the motor we need to protect it from the unsymmetrical operation somehow. Also we need to protect the motor from the short circuit. But the idea is that short circuit is usually only the result of unsymmetrical operation or overloading of the motor. So when motor working for a long time in high temperature conditions, so insulation of the motor starts to degrade, and this causes a short circuit between the windings, and then we have to disconnect that short circuit by using some of the protection devices. So, because we need to protect the motor from the unsymmetrical operation, there are several ways to do that. One of them is negative sequence relays. So, in electrical network, we can distinguish several sequences. It's positive, negative, and zero sequence. These sequences are actually mathematical thing to calculate unsymmetrical networks. But basically those sequences can be also practically measured in electrical network. So during unsymmetrical of the operation of the motor, negative sequence increases greatly, and if there is negative sequence increase, we can use special relays to disconnect motor. However, negative sequence relays are not that cheap, and usually they are used only for expensive motors. So for small motors, negative sequence relays are not used. However, nowadays when we have these data analytic things, it's possible actually to monitor temperature of the motor. So motor temperature is also a very important parameter that can inform us about motor operation state. So basically, if it's possible, instead of negative sequence, it's possible to use also temperature monitoring of the motor, and if the temperature exceeds allowed temperature level, so it's possible to simply disconnect the motor from the network. So, however, if already short circuit happened either in the motor or in the cable, which is connecting motor with the network, we still need also overcurrent protection devices to disconnect the motor. And fuse in this case is not allowed and not recommended. Why? Because fuse can, in case of fuses, when fuse is connected on each phase, there are 3 phases in the electrical networks normally. So if one phase fuse will fail, during some maybe there was some failure in the fuse itself, it's possible that only one phase fuse will fail. So then there will be only 2 phases left, so with other 2 fuses, and basically the motor will still operate. Because if the motor is already started, so 2 phases is enough for the motor to operate. However, there will be a huge asymmetry between the voltages, because one voltage will be equal to 0 and there will be 2 phases with voltages equal to nominal. So basically it creates a huge asymmetry, and when we use fuses we actually risk of getting our motor overheated because of a huge asymmetry in phases. So therefore fuses are not recommended there, and for motor protection we recommend either motor breakers, motor circuit breakers, or just normal circuit breakers with electromagnetic tripping characteristic. So here in this case I will use one normal circuit breaker of 600 amps. We can see that our motor current is 300 amps in normal operation. So this is because motor is not fully loaded. Let's open the breaker. Again, as in case of fuse, in case of breakers, we also have a library for different manufacturer breakers. The user basically can search, look through the library, select a specific model, or he can add any breaker himself. We also have manufacturers that are operating in India, like Larsen and Toubro, Compton Graves. So these are manufacturers more common in Indian markets, but Siemens, ABB, Schneider, they are most commonly well known in all the world. So you can select breaker from the library, and when you do that, then it is possible to work by changing breaker settings. So basically first we need to select the nominal value from the breaker, and one possible option would be to select 400 amps nominal, and in this case I think that it should be enough. Then we can see that it is possible to select also current multipliers and also time settings for the breaker. So these are all current multipliers and time settings are very important, because they specify how our breaker will operate. So let's go and check what are the settings we should provide for this specific breaker. So I will go back to chart curve for this breaker, and basically what I see here, I see again a normal operation curve, which is 300 amps. Then I see information about the cable capability, and this green curve, it shows motor starting time and also motor starting current. The blue curve here, it shows also motor starting time, however it's calculated with a different method. So this is a simple motor starting, and here is dynamic motor starting. So as I have mentioned, simple motor starting usually gives a more conservative current. It is a little bit bigger. However, it does not allow to estimate motor starting time. Therefore, we don't know how much it will take for the motor to start. So first of all, we need to make sure that our protection device has enough safety margin from our current here, normal operation current, and our pickup current. So I can double click on the line, and I can increase the current multiplier by choosing those arrow buttons here. So I will increase current multiplier maybe to 0.9 times the nominal current, and it is also possible to check whether it would be optional to reduce time setting for my protection device, and maybe to optimize protection coordination a little bit, because our main goal is to set protection devices sensitive enough to actually disconnect as fast as possible. We can see that when I reduce time setting, so my protection device in this area here has cross-section points with the motor starting curve, which means that during motor starting it is possible that my protection device will trip, which is of course not good, because motor starting should be allowed. Therefore I will double click on the line one more time, and I'll increase time as it was before, so to 12 seconds. Now I also have to select a short time stage current setting. So basically I see that current multiplier is 6.5, and if I reduce current multiplier so to 5.5, so I will move closer my breaker characteristic to motor starting curve. If I increase, so I will have a bigger safety margin. So because I see that recommended calculated motor starting current by the simple starting method is a little bit bigger, so I would like to put some safety margin from dynamic motor starting current, so to avoid any tripping during motor starting. Also I can set short time stage time operation, and here it's 100 milliseconds, and basically it's a minimum that is allowed to set for this protection device. So I can only increase, but increasing this time would be not necessary, so I will leave 100 milliseconds as it was before. And here we go, here we have protection coordinated for our motor. As I have mentioned, don't use fuses for the motor protection. Motor breakers or normal circuit breaker should be used in order to avoid unsymmetrical voltage for our motor. Let's go further on and now talk about the capacitors protection. So here we have capacitors with harmonic filters. However, the biggest problem which affects capacitors is actually harmonic currents that overload the capacitor and increase its temperature. In order to avoid harmonic overloading for the capacitors, it is recommended to use automation devices, actually reactive power automation devices that have built-in harmonics measurement, and according to predefined limits for the current and voltage harmonics, they disconnect the power bank if these limits are exceeded. So the best protection for the capacitors from the overloading is basically reactive power bank automation device. However, we also need to protect our capacitor bank from the short circuit. So for short circuit protection, we can use fuses as one of the most cheapest protection type. What we need to make sure is that each step of the capacitor has a separate fuse. So it's not possible to provide to put only one fuse for, let's say, the whole power bank. So you can see that I have two steps here. Yeah, here's my power bank of two capacitors, and each of the capacitors have separate fuses. So this is very important to ensure protection of each capacitor, because normally if only one capacitor is affected by the short circuit, the current won't be big enough for the fuse to disconnect if you select very powerful fuse. What is more, we need to have a backup protection for our automation device. So it is also recommended to use overload protection device. So here, this is a thermal relay, which in case of uses overload will disconnect the whole system here, the harmonic filter and the fuse and the capacitor itself. So we have even two protection devices connected. So let's open the system and see how to set two protection devices. It is very easy. On the left side, actually, you have a broad list of different protection devices that you can add, and just by adding protection devices from the list, let's say I can select fuse and I can select overload protection. If I need, I can also select like ground fault protection or voltage protection, so I can select as many protection devices as I want in this list here. So now I selected two protection devices, fuse. So already I have shown how to select the fuse. Let's check overload protection. And for overload protection, again, we have a library for different manufacturers. So Siemens AT and AT in this case. So basically you only need to select the protection device itself and also to select its nominal current. So overload protections have only one parameter, which is nominal current usually. So I will select 150 amps. Let's go to characteristic here, and let's say maybe 100 amps will be enough. 100 amps will be enough actually. So here in the red line it shows normal current. Here we can see that we have our overload protection device time and current curve, and in case of fuse current exceeds calculated maximum current, so the overload protection device will trip in order to avoid overheating of the fuse. So this kind of thing can happen in case of high harmonic levels. Also, if insulation of the fuse will be affected, so the current will also increase, and this overload protection will disconnect the fuse and will protect the substation from the fire. Let's say if fuse will explode after the short circuit. Then we have the fuse curve here, and this fuse curve specifically protects our system, our capacitor from the short circuits. You can see that these two protection devices they work nicely and protects the whole system from capacitor overload, as well as they protect the cable of the capacitor. So in case of short circuit, fuse will very suddenly blow in a short amount of time and will protect the capacitor itself. So here we have discussed main protection devices for main equipment in the low voltage side. And of course each protection, as I have mentioned, should have a backup protection. So the backup protection in our case is this Inverter breaker here. It's quite a big breaker, 3.2 kiloamps nominal current. So this breaker should work selectively with all the protections which we have shown here, which we have analyzed here. So I will double click on the breaker here. Already settings for the breaker are provided. So breaker won't trip during motor starting, and here we also have information about transformer capability curve. You can definitely see that transformer capability curve is bigger than our breaker chart, and therefore during short circuits our breaker will disconnect before the transformer will overheat. So how to select selectivity within our software? So you can do in this way. When you have a single line diagram with other protections created, you can simply take any protection devices from the network and you can put on the same single line on the same protection selectivity chart with the incomer breaker. So now we have our incomer breaker, and we have our fuse. So you can see that fuse curve is quite far away to the left side, which means that our fuse is selective with our incomer breaker. Okay, now let's select, I will deselect the fuse and I will add this breaker here to make sure that my incomer breaker is selective with this breaker here. I will put the breaker curve. Okay, so I can see that my motor breaker again has a lower pickup rating. It has a lower operation time, and in case of short circuit also it has lower operation time. So my incomer breaker will wait for other breakers to operate, and in case those other breakers won't operate, so then incomer breaker will operate. So I believe that this kind of protection will work just fine. It is selective and with minimum time settings. So what we can do next in this kind of network, actually we can also select arc flash conditions to make sure that arc flash is within the permissible limits. So let's try to calculate arc flash in bus 7. So I will double click on the bus bar. Installation type for this bus bar is MCC and panels. So okay, so it's motor control center or panel. So let's assume that this is a panel for our loads, and let's calculate arc flash in bus 7. So software will estimate the short circuit current and also disconnection time for the short circuit in bus 7, and will estimate incident energy in working distance as well as possible flash boundary. So let's look quickly through these parameters here. So first of all, we have information about the fault current. Fault current is quite huge. It's around 42,000 amps in case of maximum three-phase short circuit. Arc current is a little bit smaller. It's about 25,000 amps. So installation type is MCC and panels, as I have shown before. The network is grounded, so these parameters are needed for arc current calculation. Then we have clearing time calculated. So according to settings that we made, clearing time is around 300 milliseconds or 0.3 seconds. And the flash boundary is around 3 meters, so it means that safe distance to stand from the bus bar in case of this huge fault current would be about 3 meters. So basically it's quite a huge distance, and maybe we will need to take some actions to reduce this flash boundary. Then working distance is estimated as 45 centimeters. So this is a standard value, and we haven't changed it. And incident energy at the working distance is over 113 joules per centimeter square. So it means that this kind of energy will affect person's skin if he will work at 45 centimeters distance from the bus bar. So in case of the short circuit, so it's actually quite a huge energy, and it will cause a high level of burn. So we have a warning label, which should be used and which should be sticked to the panel in order to inform a person who is working with the electrical network about the possible damage, about the possible dangers. So you can see that flash boundary, as I have said, 3 meters, and in order to work with this kind of network, we have recommendation to use class 4 personal protection equipment. It would include cotton underwear plus fire-resistant shirt plus fire-resistant pants, and also multi-layer flash suit. So in order to work in this kind of network with this kind of short circuits, we need to use a multi-layer flash suit, which is not very convenient actually. If you want to do some measurements, you have to have this flash suit, you have to work with it. So we can try to reduce short circuits in order to avoid this kind of high flash boundary. So how it is possible to reduce short circuits in the network? So it's very easy. We have to increase the impedance of the network actually. So instead of this line here, let me delete this line, I will add series reactor. Series reactor, best to use series reactor actually in the medium voltage side, because here we have smaller currents and this will cause smaller losses. However, just to give an example, I will connect this series reactor also in low voltage side here. So let's see what the parameters can be. For the reactor, let's take 4% short circuit voltage. Nominal power should be equal to our transformer power, let's say 2 megawatts, and short circuit power I will, let's say, provide 5 kilowatts. Okay, so we have series reactor connected, and when we will calculate now all the parameters regarding also short circuits, let's go through arc flash calculation as well with the series reactor connected. Okay, so calculations are done. We can see first of all that flash boundary was reduced by almost half a meter. Yeah? Fault current was also reduced. Instead of 42 kiloamps, something like that, now it's only 30 kiloamps, so much smaller. And incident energy was also reduced. And okay, so we have reached our goal. Actually, this kind of reactor would be enough to reduce flash boundary, so that in order to work with this kind of network, class 3 personal protection equipment should be enough. And class 3 personal protection equipment is only requiring cotton underwear plus fire resistant shirt and fire resistant pants, and plus fire resistance coverall. So now we don't need the flash suit, which is good. We only need the fire resistant fire face coverall, and this will be enough for us to protect the person from the severe damage in case of a worst case scenario, or in case of short circuit in the electrical network. So we can see that with software it is possible to calculate technical things in order to protect not only the equipment, but also in order to protect the persons who are working with the network. So I think that we can do a quick break in order to read the questions. So first question was provided by Palash, and my colleagues already, I think, answered the question. The question was, is it possible to get this protection coordination module to those who registered for webinar? So it's not a technical question, so just please contact our info@energyadvice.lt site, or just visit our site and download the version for calculations. So let's look at the next question. How much difference between this asymmetrical fault and symmetrical fault can damage any equipment? So basically symmetrical fault is only one, so it's a three-phase short circuit current. Usually this is the biggest short circuit current, which causes not only an electrical overheating damage, but also mechanical damage to the equipment, because when we have huge currents in the network, so basically this causes actually mechanical forces between the equipment, and okay, this can damage like contactors. This can damage also isolators by simply breaking them. However, asymmetrical short circuits like one phase, two phase with ground, they are more often. Like three-phase short circuit is not that often. It happens from time to time, but it's quite rare. While one-phase short circuit will happen quite often in the electrical networks. And this kind of asymmetrical short circuit, it also overheats the equipment. Also, like I mentioned, it's very damaging to motors that cannot work only by several phases operating, and the inverters cannot operate, so it's hard to say which damage the equipment more. Actually, both of them causes problems. However, symmetrical short circuit is usually providing most of the problems. It's because it provides biggest short circuit current. So the next question was, while motor starting analysis, why not considering transient voltage dip parameters? So when we do motor starting analysis, software automatically evaluates voltage dip in the network. And for example, if I open, let's calculate motor starting one more time, because I changed the network a little bit. I added this reactor here. So let's calculate motor start dynamics one more time. So software automatically evaluates actually a voltage dip which is created during motor starting. So when the calculations will be finished, I will just quickly show you. So here are the current values. However, let's check voltage values in our main bus bar. So let's say bus 7, which is the main bus bar where my motor is connected. So bus bar 7, yeah. So in case of bus bar 7, we can see that during motor starting, the voltage was around 334 volts. Yeah, but after some time, after the motor was started, the voltage went back to normal. So here, this graph explains voltage dip phenomena during motor starting, and all the other currents during this motor starting will increase. So if I'll open the inverter current, so we can see that during motor starting, the inverter current was a little bit bigger than during normal operation. This is because during motor starting, voltage was reduced, and in order to transmit the same amount of power, current have to increase. So the current is bigger here during motor starting, then it goes to the normal value. So software definitely evaluates motor starting and also voltage dips during motor starting. Next question, is it possible to show the cable capability in the TCC curve so we can see if primary protection fails, backup protection detects it? So definitely when we open TCC curves, so we can see the cable capability. This is the breaker. This is the cable which is protected by the breaker. And basically this is our transformer. So we can see that our backup protection is not fully protecting our cable. So in order to optimize this, we can try to reduce the time here. Yeah, so I have, however, only two time settings, like 3 and 12 seconds. So maybe I'll just set 12 seconds and leave as it is. So I need to look for another breaker which would allow me to provide some settings which are like smaller than 12 or bigger than 3 seconds. So, but the idea is this, that in our software you can also add cable capability curve and selectivity charts, and ensure that backup protection will also protect the cable. The one more question was, is it possible to simulate lightning phenomena on EA-PSM? So yes, it is possible. We have electrical electromagnetic transients calculation feature. However, this is not the topic of today's seminar. So, but the idea is that you can do that, and basically you can also select surge arresters in order to protect equipment from lightning phenomena. There was one more question in explanation if it is projecting IEC or IEEE parameters and good for understanding. Yeah, so calculations are done according to IEC standard, and in case of protection devices, so we have protection devices capability to add protection devices made according to any either IEC or IEEE standards. So yeah, we are considering these standards. There was one more question, how to calculate DC component of circuit breaker during asymmetrical short circuit. So DC component calculation during asymmetrical short circuit is not calculating because worst case scenario is during symmetrical three-phase short circuit calculation. So when I calculate three-phase short circuit, I can go to peak values of the short circuit, and I can see that in each case of short circuit, let's say we have short circuit at bus 7, so software provides information about DC short circuit current component in the 0 time. So basically it is equal to 42,000 amps. After 100 milliseconds it will be equal to 475 seconds. So these DC components of the short circuit current are calculated in worst case scenario, and the methodology for calculating these currents uses resistance and reactance of the network, which is automatically calculated from the data provided by the user. So DC components actually can be calculated. One more question. What are the parameters that should be considered while selection of the main equipment like circuit breaker? So main parameters, as I have mentioned, is first of all power flow current. So power flow current, let's say 577 amps. So circuit breaker should have a bigger nominal than the calculated low flow current. Here we can see that calculated current is quite much smaller than the nominal value of the breaker. This is because we have equipment which is not representing full loading of the transformer, and breaker was selecting by evaluating full load. So if I'll disconnect all this equipment and because the transformer is 2 megawatt, I will connect lump load here, and I will specify that this load is 2 megawatts. So when I will connect this lump load, so I will see that current is 2800 amps if my transformer is fully loaded. However, if you evaluate some overload conditions as well, let's say I will add some reactive power, so current can reach about 3000 amps, and because of that we selected the breaker, which is 3200 amps. Later on, when we have breakers selected according to our transformer, we can select settings for the breaker according to normal current. The normal current is much smaller because now our transformer is not fully loaded, so 577 amps. Therefore, when I open the breaker, I have a current pickup value multiplier set to 0.4. Means that software automatically multiplies 0.4 times 3200, and the pickup value is set to 1280. So these multipliers are used to align breaker to actual load, but nominal rating should be selected according to the transformer power. And then there was question about standby earthfall protection. So I will talk about the earthfall protection. What is the time margin for the coordination? Basically, recommended time margin it should be around 150 milliseconds. But if you use the same manufacturer equipment, like same manufacturer breakers, like in this case I have a ABB breaker and ABB breaker here, so even smaller time margin can be used, and in this case only 100 milliseconds is used. But in our software, actually what you should take into account is these dashed margin lines. They show the possible operation time margin for the breaker. So breaker in theory should operate by this solid curve. However, because no equipment is no equipment is ideal, and it will operate with some error, so time margin is provided by the dashed lines. So if those dashed lines are not having cross-section points, so like here I can see that my dashed line of the first breaker ends here and then starts like second breaker dashed line, so it's okay. So basically these two breakers, they have like enough time margin. But as I have mentioned, if you will use different manufacturers' circuit breakers, so then at least 150 milliseconds time margin is required. What is more, if you are using mechanical relays, so like almost half a second would be required because of the huge time margin that they need, because these are not very exact equipment. But nowadays all the electromechanical breakers also relays, numerical relays, 150 milliseconds would be enough. So the question about how software is different from the others in the market, maybe I will not answer, it's not the topic of today's seminar, but during the presentation, so I think that you will get most points. For example, in our software you are capable to make the report, so like not in all the softwares it's possible to do that. Then user support, trainings are cheaper and things like that, so it's not the topic of today's trainings. The question now, for setting a short circuit protection for transformer inrush current, or short circuit current, consider it, which is a good safeguard to the transformer. So transformer protection is a little bit more advanced topic. Usually in order to set transformer protection, we use numerical relays, which are capable to measure second harmonic, because during transformer launching, inrush current is very rich with second harmonics. So if you are capable to block operation of the numerical relay during transformer launching, and you can understand that transformer is launching because of the second harmonics flow, so then operation of the numerical relay for the transformer just set in a normal way. So all you need to do is to block a numerical relay operation during launching, and you need the second harmonic measurement for that. But even in this case, it's not that important, because in some markets I know that the transformer is launched several ways. So you just connect the circuit breaker, transformer will charge a little bit, the breaker will disconnect, then you connect breaker one more time, and in several times you are capable to launch the transformer. Of course, if transformer is very big, so it's also possible to use generator to charge the transformer, and then when you will connect to the network, so inrush current will be very small. So there are very different ways on how to connect the transformer, and maybe again during today's trainings, because these are only 2 hours trainings, I will not cover all of them. You have exchanged data with PSCC and NAPLAN. So yeah, actually there are formats that that allows to exchange data. And then one more question was, do we have digital relays? Also yes, and I think that now we can go to relays modeling in the software. So basically the next topic will be regarding the relays in medium voltage network. So for relays, first of all, what we need to select is the breaker. So because the relay is automation device that needs to control the breaker, which will disconnect the network. So first of all, we need to select the breaker, and in order to select the breaker, we have recommendations from the software. For example, for this transformer breaker, or let's take maybe not the transformer, because here already I have the protections selected. Let's take this motor. So the motor current is 56 amps, and when I open the breaker, so I can see that I already have recommendations for my breaker. So for example, nominal current should be 63 amps. This is bigger than normal current of the motor, which is good. So our breaker should have bigger nominal current. Voltage level is 7.2 kilovolt. So you see that our network voltage is 6.3 kilovolts. However, nominal voltage of the circuit breaker is bigger. This is because during single phase short circuit, voltage will increase significantly in this kind of network due to voltage drop in the grounding resistor. So here I have 9 ohms grounding resistor, so therefore voltage will increase, and our breakers should be capable to withstand this voltage increase, and therefore software already recommends bigger voltage nominal than network voltage nominal. Also, I have recommendation for maximum short circuit current. It's 20,000 amps. So this is recommended according to short circuit calculations. Peak short circuit current should be over 50 kiloamps, DC component over 25 kiloamps, and breaking current around 20 kiloamps. So all these parameters might be needed for breaker selection. So relay, breaker, we also need current transformer for full operation of the system. So let's go to equipment, and in the first tab here we have current transformer selection capability. So I will add one current transformer to the network, and in order to select current transformer, actually we need to select the transformer transformation coefficient. Like basically now the transformation coefficient is 400 amps. So we need to make sure that we know what is the wire length between the current transformer and the relay. So let's assume that wire length is 15 meters. Wire cross-section diameter, let's say, is 2.5 millimeters square. Transformer power, let's assume that it's, let's say, 15 volt amps, because we'll connect only single relay, so we don't need a very powerful transformer. Then internal resistance. So as a rule of thumb, this internal resistance is something from 4 to 6 ohms. So actually now it's 6 ohms provided here by default, and I will leave this default value. And here is relay load. So basically this is the resistance of the relay, so it's 100 milliohms. So I will leave this value. And when I have these parameters provided, so software automatically calculates what is the recommended accuracy limiting factor for the transformer, and in this case I see it's 22.3. So basically I will have to select a transformer with accuracy limiting factor bigger than 22, and it can be like 30. I can enter 30 here. Or if I want a transformer with a smaller accuracy limiting factor, I have to increase the current rating of the transformer. So if I increase transformer to 500/1, so I can see that accuracy limiting factor 17 is enough. So I can select transformer with accuracy limiting factor of 20. So accuracy limiting factor is a very important parameter because it allows to select transformer with good enough rating to avoid fault readings of the current. So if accuracy limiting factor is too small, during short circuit operation, transformer will saturate and will provide currents that are not very exact. And this might be a problem for some of the protection devices. Therefore 17 would be a good value to set. So now I have a current transformer selected. Let's go and select numerical relay. So first of all I need to select overcurrent first stage of the numerical relay. So I will select the functionality overcurrent, and also the second stage can be already added. So I will select numerical relay according to the normal operation current. It is 56 amps. So I need to provide some safety margin. I will provide, let's say, like 80 amps current. Operation time 20 milliseconds, and definite time curve. So if I provide these readings, so my protection device current and time curve, TCC curve will look like this. So it's not good because it will not allow motor starting. You need to estimate what is the motor starting here. So let's calculate motor dynamics, motor starting. In order to estimate what is the motor starting time and motor starting current. So motor starting time we can see around 6 seconds, motor starting current around 263. So now we know the motor starting parameters, and according to those parameters we can try to set the time rating for our numerical relay first stage. I can increase, for example, time setting over around, let's say, 9 seconds with some margin. Again, we are not exactly sure. Maybe motor during some of the operations will take more time to launch. Therefore, we have to provide some time margin here as well. Now we would like to add another step for like second step for our overcurrent numerical relay, and I would say that current could be around 350 maybe amps, and time setting could be minimal. I will add the second stage. In order to represent that this is the second stage, I will add one more sign here, and as I have mentioned, current setting I will provide 35 amps, and the time setting I will provide minimal. And in order to make curves look nicer, so I will connect them. So like this I have a numerical relay with two definite protections, definite time protection stages, and I can see that this numerical relay won't trip during motor starting. It will also protect my motor in case of short circuits, because in all the points my TCC curve is smaller than the capability curve of the cable. So here we go, we have set like two stages for numerical relays. What we would like to do as well, maybe we would like to add something like under voltage relays for our motor, because let's say if we'll have under voltage conditions during short circuit or during other motor startings, so motor speed will go down, and after the voltage will get normal, motor speed can very quickly start to accelerate, and this will cause high inrush currents for the motor. So to avoid that, we might use under voltage relays. So I will double click on the breaker and I will add one more numerical relay option, which is under voltage relay. So I will add two different stages for the under voltage relay. So for the first stage, let's select that our numerical relay will measure phase-to-phase voltage. And let's see that, let's say, in case of voltage will go down by 80%, by 20%, so the voltage will be 5000 volts around. So our relay should trip in, let's say, 15 seconds. For this motor, to avoid high inrush current during self-acceleration of the motor. Then for the next stage we will set even lower voltage drop, let's say 40% voltage drop. So the voltage will reach 3700. Yeah, and then in this case of high voltage drop, our tripping time should be faster, let's say 3 seconds. So 3 seconds will provide enough time margin for overcurrent protection devices to operate. If overcurrent protection devices won't operate, so after 3 seconds the motor will be automatically disconnected to avoid high inrush current after motor acceleration. Let's go further on. In this kind of network, as I have mentioned, we have smaller earth fault current because we have this resistance grounding. So let's calculate short circuit in bus bar here. So we can see that like 3-phase short circuit current is over 12,000 amps, 2-phase is 10,000 amps, and 1-phase short circuit current is 349 amps. So you can see that 1-phase short circuit current is much smaller. So therefore we need different kind of protection devices in order to provide protection for the network from this 1-phase short circuit current. And this kind of protection devices can be ground fault currents. So I will go to the display options. The thing is that ground fault currents, they measure zero sequence current and basically 3 times zero sequence current. So in order to set earth fault protection devices correctly, we need to set them according to zero sequence currents in the network. So I will select for the software to represent zero sequence current. Yeah, so I can see that the currents have changed. So now in case of 1-phase short circuit, I have a current equal to 120 amps, and this is a zero sequence current. So earth fault protection device, it measures 3 times zero sequence current, so 384 amps. So let's check what will be the zero sequence current if I will have short circuit here. You can see it's about the same size, 125 amps. So when I set my protection devices, earth fault protection devices, let's add the earth fault protection devices. I will also add 2 stages. So first of all, we need to set time, let's say, for the first stage. So first stage name will be current, earth current more. And here I will set time, let's say 3 seconds, and 3 seconds will be in case earth fault current is equal something to like 5% from the nominal current. So this is to avoid the protection tripping during normal operation, and earth fault protection can trip because of like error of the zero sequence transformer. So error can be around 5%, and during normal operation zero sequence transformer measures normal current. So we can see that in case current is more than 3 amps here, so our disconnection time can be around 3 seconds. So it means that there is some problem, but not maybe that big, maybe some voltage current discharge somewhere. So we should wait for quite a long time, even 3 seconds, and not to trip instantaneously. However, if our current is exceeding zero sequence current, So it means that we definitely have a short circuit in this line, because imagine, like, for example, if we have short circuit in bus 6, we can see that current in this line is 125. However, in all the other lines current is much smaller, so here like 0.11, here is 0.18, so very small currents. So we need to set current which is actually bigger than the rating, actually not bigger, smaller than the zero sequence current, but with enough margin to maintain selectivity. So I will provide something like, let's say, 150 amps, and relay time setting I will provide quite small. We can set here like 100 milliseconds. What we also need to check, what is the self-capacitive current of this line. So when we calculate short circuit in any other line, so we will get self-capacitive current of this line, and it is equal to 0.05. So basically, if I'll multiply this by 3, 0.05 times 3, it's equal to 0.15. So we also need to make sure that our earth fault setting of the first stage, we set 3 amps here, it also need to be bigger than self-capacitive current. So these are several important criteria to check. What is the self-capacitive current, what is the error of zero sequence transformer, and according to this we can set ground fault current rating. So here I will provide the name of earth fault current 2 times more. So basically, for this motor I have provided numerical relay with almost six functionalities. So it's overcurrent, undervoltage, and also earth fault current. So in software it is possible to add not the protection device itself, but only functionalities of the protection devices. So you provide the functionalities, and these functionalities can be used in any other relay. Actually, you can provide these functions by adding data you have set to the relay, and it will operate according to the user's needs. Now let's check selectivity coordination of this relay with main incomer relay. I will double click on the main incomer relay. I will recalculate more time the short circuits and also load flows. And here I will open the setting. Okay, so we can see that here we have the current TCC curve of the main incomer device. What we have to try to do, we have to add the motor relay in the same picture to see whether these two relays are selective. You can see that motor relay is definitely under the main incomer relay, which is of course good. What I see here is also that main incomer relay is also constructed of 2 stages, and basically one stage here it has 190 amps setting. Second stage here has let's see, around 300 amps setting, 500 amps setting. And the second stage is not blocking the first stage, because in case of this area here, I can see that first stage is also covering second stage, which is maybe not good. Normally second stage is blocking the first stage. So I will double click on the second stage TCC curve, and I will activate lockout of the first stage. Yeah, so now the second stage, because it has bigger current rating, it will block the first stage here. Let me see also the current calculations. we have a current of 500 amps flowing through the transformer. Here we have 37 amps, 56 amps here, and this generator connected here, it provides 500 amps. So I believe, according to the information of the current which I see here, yeah, my normal current quite extensively exceeds the relay setting. This is because my relay setting was done without this generator. When this generator is not in the network, yeah, so then we can see that our current is much smaller than the setting of the our relay, and the system works just fine. But when we connect the generator, yeah, the current increases and then exceeds our breaker setting. So in order to solve this, we need to also increase the settings of the relay here. So first of all, I need to increase the settings of the first stage. So I will provide something like 600 amps with the generator, and then I need to increase the settings of the relay here. So I will provide something like 1000 amps. So now my incomer relay will not trip during normal operation of the system. In order to protect cable, I also need to reduce actually time setting for the very inverse time curve. So I will provide the time setting of, let's say, 0.5 seconds. And I can also see that my cable has not enough, my cable capability is not enough to transmit current even in normal operation. So therefore I will have to go here, and I will have to select a different cable with enough capability rating. So I will select first of all voltage level. Then I have the library for the cables like polycap, Nexans, and different cables. So I will select maybe 300 millimeter square. So what is the rating of this kind of cable? Let's check. So ground temperature, burying depth. So I need these parameters in order to calculate current rating. So 426 amps. I need like 2 parallel cables here, like this. So my cable is selected, and now I can see that my cable capability is enough actually for my relay. Here is the capability of the motor, which we have worked with the protection. The motor was here. So in software it is possible to select cables, their capability limits, and select protection settings so that they will protect the equipment. However, when we do the protection coordination, so we also need to check how our protection coordination will work in case of different scenarios. So for that reason we have protection tracking feature. This is a feature which allows to simulate different scenarios in the network and to see operation of the protection devices. So let's try to simulate bus 4 and bus 5 short circuits. Bus 4 and bus 5. So when we do this kind of simulation, software provides information about what are the protection devices tripping in each case. So if I have short circuit at bus 4, so I can see that this line have tripped, and the protection device which have tripped is IEC very inverse curve. So this curve tripped in this protection device tripped in 315 milliseconds. In case of bus 5 short circuit, so bus 5 is basically here in between the solar power plant and the main bus bar. So 2 protection devices have tripped. First of all, overcurrent protection device on the line here have tripped, and later on voltage protection device which is protecting solar PV plant have tripped. So the operation, as we can see, first overcurrent protection device, and after 300 milliseconds under voltage protection device. So this protected power system from working into bus bar, which is not connected to the network. Also, we can simulate generator protection operation. So generator is connected to bus 19. So from the list here, we can select bus 19 as well. This I will disconnect. So in case of bus 19, what have tripped is basically relay here. It disconnected the bus 19 from the rest of the network. And I can see that generator is protected by the directional protection devices, and the forward direction protection device have tripped. So basically, if I'll open overcurrent protection devices of the generator here, I can see that there are two overcurrent curves provided. And if we'll go to protection devices settings, before that I will also recalculate short circuits. Basically, I will show quickly about the directional protection devices. So there are two types of directional protection devices, directional forward or reverse. So basically, one is protecting the generator, another is disconnecting generator from the network in case we have short circuit there. So in case of forward direction protection device, we can see that all the short circuit currents are looking like that. So these are vectors of short circuit currents, and they are inside the blue area, which are representing the directional protection device operation zone. So I select user actually manually have to select this zone. He gets, of course, recommendations how to do that in order to set directional protection devices. In case of reverse directional protection device, I have much more vectors, so of all the short circuits that are happening in the network. So I have selected my operation zone so that the directional protection device will sense most of the short circuits in there. So we can see that all those vectors are mostly in the blue zone, which says that with these settings, my directional protection device will correctly measures the direction of the current, and it will trip with different times. So the difference is that directional forward relay is tripping in minimum time, which is 20 milliseconds, and directional reverse protection device is tripping in 300 milliseconds, because we need to also maintain selectivity with other protection devices. However, forward direction protection device does not have to maintain selectivity with other protection devices, therefore time here is minimum. So in software also user can set directional protection devices. Earthfall directional protection devices can be also used. However, as I have mentioned, this is a very broad topic, so we cover all these things during EA-PSM Academy. What is more, we also have distance protection, which allows to work with high voltage networks protection coordination. So the last thing that I would like to show regarding the protection coordination today is project panel. So basically, inside the software, user is capable to make a report regarding the protection coordination or any other calculation. So here is the project panel button. So when I open the project panel window, so it opens me the PDF report where I can change information. Let's say what is the factory name and address, what is the company name, date of the protection report. Here you can provide also information about the company, project name, and other details. It is possible inside this PDF automatically import information about the equipment in the network, also about the calculated information. So for example, here in this page I have network data, and here cable lists provided, motor lists, transformer lists, and things like that. The good thing about this feature is that if you make any changes to the network, so basically you don't have to change all the report. You can automatically change only the single table. So you remember that, for example, I added cable here between section 2 and substation 1. So now I can add this cable. So let's see, section 2, substation 1, it's here. Yeah, so my table just automatically expands with one more cable which I have specified. So it was Nexans cable, 2 conductors, single phase, single conductor cable. So basically I can also a little bit change the length of the columns in order to fit all the information in the table. I can also add information regarding the calculated results. So in the protection coordination report, you have to provide information first of all about the motor starting. For example, here you can see that there's zeros, but if I will calculate motor starting currents, motor start simple, so information will automatically go to the table. You can also prepare something like a example of the report and just change the single line diagram, recalculate the things, and the report will automatically change accordingly. Also, you need to provide information about the short circuit currents, and here I have short circuit currents in maximum and minimum mode in all the possible scenarios. So it's 3-phase, 2-phase, 1-phase, and 2-phase with ground short circuits. So again, this table was added automatically. Let's delete it from here and add one more time. So I go to table, I go to short circuit all branch results, and here we have the table already added. So in order to add this to your report, you have to export to Excel. You have to then add into Word document, while here in EA-PSM you can automatically add the table directly into PDF. Here I also have information about load flow results. So load flow results should be also added to the table. So basically these are three most important result types. So load flow, short circuit, and motor starting results that you need to provide in the protection coordination report. Later on, you can provide information about single line diagram. The most common way to provide information regarding the protection coordination settings is to provide part of the single line diagram with the considered breaker or the relay, then to provide settings of the breaker and also a TCC curve of the breaker. So again, in software you can do this kind of things automatically. So like you can add the single line diagram. You can specify what kind of the results should be represented on the single line diagram. It can be short circuit currents. It can be power flow results. Then you can add the breaker itself. So this is the data about the breaker, and then you can add basically a single TCC curve of the breaker. So let's add maybe one more example. So I will add one more page. Let's go to the network here. For example, I will highlight the inverter with the fuse and the cable. Yes. So I will add the scheme view for the inverter. So the bus bar will be normal size, but you can always reduce it and increase the single line diagram size. Now I can add information about the power flow results in order to provide for the customer. Now I can also add the fuse itself. So let's go to protection, fuse. Here's the list of all the fuses in the network. basically all of them are connected to bus 7, so I can use also filter to select the particular fuse. Yeah. Some of the columns of the fuse are not needed, so I'll just simply disconnect them. So let's say I don't need information about the element, breaker, gauge, type. Maybe only this data for me is interesting. Yeah, so here's the information about the fuse, and I can also add the fuse curve. So bus 17 and line name bus 7, bus 8. So from the list here is this is the breaker. Yeah, so this is the fuse curve. So I can increase the characteristic of the fuse. I can align so that it's in the same location as this one, and basically one by one I can create create the report about all the protections. I can add also numerical relays, motor starting data, and other things. Everything is already calculated. We just need to add the data into the report. So you don't have to export anything from the software. Everything can be done here inside the software itself. You can add the pages. Pages have numbering as well, so you can change also the pages orientation if in this way also. So basically a report can be created inside the software, and when this kind of report is done, so you can export this to PDF, yeah, on any location. Let's say desktop, save, and you will have the report exported on the PDF on the desktop. So now basically regarding the questions, I think that I will open the contact details about our company, and I will look also to the questions. Maybe some of the questions I can help to answer, and I think this will be enough for today's presentation. Actually, protection coordination is a very broad topic, so for more details, of course, we need a little bit more time. There was a question about explaining further if it is possible to import data in the software from other softwares. So basically you can import using CDF format, industry standard format, to import from one software to another. So in PSCC you can export CDF and then import into our software. The problem regarding the format is actually that it does not include any information about the protection coordination devices. So still you will have to add the protection coordination devices manually. But for example, PCC software does not have a protection coordination like we have in our software. So it's not that a huge problem. So if you want to import from PCC, you can use the CDF format and then add the protections manually here with our software. Then there was one more question. The question was if software can support overload release magnetic protection and also for static multifunction relay. So basically, let's cover maybe quickly what are the options that users can include in our software. So first of all, it's overcurrent relay. Any number of stages, also directional overcurrent relays can be included. Then we have under voltage and over voltage relays. Then it's possible to include a motor circuit breaker. Then the ground fault relay, also directional or non-directional. Then it is possible to include fuse, circuit breaker, mini circuit breaker, also overload protection. So as per your questions, basically we have overload protection, And if there is some protection device that we don't have in the software, so we provide custom curve functionality where user is capable to specify actually TCC curve by hand and include this kind of protection device into the calculations. So the webinar was recorded, and basically you will be capable to look it in YouTube later on. So thank you, Angoni, that you mentioned that software takes complexity of what we do. So basically protection coordination is like one of the strong points of our software. So hope that seminar was helpful. And as I have mentioned, basically I showed only part of the functionality. So if we look closer on, so we have transient analysis, solar irradiance modeling, wind turbine power quality, relay coordination, basically automatical functionality for overcurrent relays coordination, protection tracking, insulation coordination, DC battery sizing, cable sizing, also DC networks design. So there are many functionalities. Also, if we need to analyze different states of the network, so we have snapshot systems where we can create different scenarios, and basically later on when we make a report, so for example we have to select which is the scenario calculated, so we can represent results from any of the scenarios analyzed. So this allows to create a comprehensive report about the network. So I think that for today's trainings this will be enough. So I specified the most important functionality regarding the software. Hope the seminar was useful. So in order to make it so we also provide some technical details in seminars, also theoretical details, and we not only talk about the software itself. So one more time, we invite you to EA-PSM trainings, which will be 16 hours full-time trainings, which covers all the topics regarding power quality, protection coordination, and details related to that. So in order to participate in the trainings, you can write to our email, or you can register in our site. Also, you can download the demo version of the software in our site. And for renting the software or buying the software, please consult us by sending email to info@energyadvice.lt. And soon we will make functionality so that you can simply rent the software without contacting us, using your credit card or PayPal account. So thank you one more time for participating. Have a nice day. Wish you a great time, and bye.